On Earth, we're used to matter being in one of three states: solid, liquid, or gas. We see it every day when ice melts into water and water boils into steam. But what happens when you keep applying heat? What happens when you go far, far beyond the boiling point of any material we know, to the temperatures found inside the fiery heart of a star? In those celestial furnaces, where temperatures reach millions or even billions of degrees, the rules of physics as we know them are completely rewritten. This is a journey into the extreme physics of matter, into a realm where atoms are torn apart and the very essence of our universe is forged. Our journey into a star's core begins by shedding a fundamental assumption that atoms are stable, indivisible units. They're not. As gravity pulls colossal clouds of hydrogen and helium gas together, forming a protostar, the pressure and temperature at its center begin to climb relentlessly. Eventually, as the temperature hits millions of degrees, the particles in the core are moving with such violent energy that their collisions are powerful enough to knock electrons completely free from their atomic nuclei. This process is called ionization, and it transforms the gas into plasma, often called the fourth state of matter. Unlike a neutral gas, plasma is a superheated soup of positively charged ions, which are the leftover atomic nuclei, and negatively charged, free-roaming electrons. This sea of charged particles gives plasma some very unique properties. It's electrically conductive, and it responds powerfully to electric and magnetic fields. While we only see it on Earth in rare flashes of lightning or the beautiful curtains of the aurora borealis, plasma is, by a huge margin, the most abundant state of ordinary matter in the entire universe. An estimated 99.9% of the visible cosmos, from the solar wind that streams past Earth to the glowing interstellar nebulae and the stars themselves, exists as plasma. The core of a star is an environment of pure, unimaginably dense plasma, and this sets the stage for the most powerful creative force in the universe: nuclear fusion. Inside this plasma core, a constant battle is raging. On one side, you have the immense force of gravity, trying to crush the star into an infinitesimally small point. Counteracting this is a tremendous outward pressure, generated by the energy released from nuclear fusion. This delicate balance is called hydrostatic equilibrium, and it's what allows a star like our Sun to remain stable and shine for billions of years. So what is this engine? Nuclear fusion is the process of combining two or more lighter atomic nuclei to form a single, heavier one. This might sound simple, but it requires overcoming a massive obstacle: the electrostatic repulsion between positively charged protons. You know how the poles of a magnet push each other apart? Protons do the same thing, and they resist being forced together with incredible force. Stars overcome this barrier in two ways. First, the sheer temperature of the core, reaching at least 10 million Kelvin, gives the protons immense kinetic energy, causing them to move at furious, relativistic speeds. But even at these speeds, most collisions aren't energetic enough to break that repulsive barrier. This is where a second, crucial, and frankly bizarre principle comes into play: quantum tunneling. Quantum tunneling is a phenomenon that allows a particle to occasionally pass through a barrier that it classically should have enough energy to overcome. Think of it like this: if you throw a tennis ball at a brick wall a million times, it will never go through. But if that tennis ball were a proton, and the wall was the electrostatic barrier, quantum mechanics says that once in a while, the proton will just appear on the other side of the wall, as if it tunneled straight through. In the stellar core, quantum tunneling gives a small fraction of protons the chance to get just close enough for a different, much more powerful force to take over: the strong nuclear force. This force, though it only acts over incredibly short distances, is powerful enough to bind the protons together, overcoming their repulsion and releasing a tremendous amount of energy in the process. And where does this energy come from? It comes from mass. The resulting helium nucleus is ever so slightly less massive than the sum of the original protons that formed it. This tiny amount of missing mass hasn't vanished. It's been converted directly into a huge amount of energy, according to Albert Einstein's famous equation, E equals mc squared. Given the quadrillions of fusion reactions happening every single second, this process generates the colossal energy that makes stars shine. In stars like our Sun, this happens mainly through a process called the proton-proton chain, where 4 hydrogen nuclei are eventually converted into one helium nucleus. In stars much more massive than our Sun, a different process called the CNO cycle takes over, using carbon, nitrogen, and oxygen as catalysts to achieve the same result. This stellar engine isn't just producing heat and light. It's a cosmic factory, performing a kind of alchemy known as stellar nucleosynthesis. This is the creation of new chemical elements inside stars, and it's responsible for producing nearly all the elements in the universe heavier than hydrogen and helium. The famous statement by astronomer Carl Sagan that we are made of star stuff is not poetry. It is literal, scientific truth. The carbon in our cells, the oxygen we breathe, the iron in our blood. Every heavy atom in your body was forged in the heart of a long-dead star. This process happens in stages. For most of its life, a star fuses hydrogen into helium. When it runs out of hydrogen in the core, gravity compresses the core, heating it up until it reaches about 100 million Kelvin. At this temperature, helium fusion begins through what's called the triple alpha process, where 3 helium nuclei are fused to create a carbon nucleus. Once carbon is present, a new series of reactions can begin, successively adding more helium nuclei to create heavier elements. Carbon fuses with helium to make oxygen, oxygen fuses with helium to make neon, and so on, stepping up the periodic table. This chain of fusion continues, creating progressively heavier elements. However, this process has a definitive endpoint. That endpoint is iron. The fusion of elements lighter than iron releases energy, which supports the star against gravity. But the iron nucleus is one of the most stable in the universe. Fusing iron into anything heavier doesn't release energy. It actually requires an input of energy. So when the core of a massive star becomes predominantly iron, its nuclear furnace shuts down for good, and gravity, which has been held at bay for billions of years, finally wins. What happens next is one of the most dramatic events in the cosmos, and it leads to the creation of the most bizarre forms of matter imaginable. The outcome depends entirely on the star's initial mass. For low to intermediate mass stars like our Sun, the end is relatively gentle. After exhausting their fuel, they shed their outer layers, creating a beautiful glowing structure called a planetary nebula. What's left behind is the inert, superdense core, a white dwarf. A typical white dwarf packs a mass comparable to our Sun into a volume roughly the size of the Earth. The density is staggering, on the order of a metric ton per cc. A single teaspoon of white dwarf material would weigh as much as an elephant. Gravity is immense, but the star doesn't collapse further. It's held up by a purely quantum mechanical force known as electron degeneracy pressure. This pressure comes from a fundamental rule called the Pauli exclusion principle, which states that no 2 electrons can occupy the exact same quantum state. In the crushing environment of a white dwarf, all the low-energy states for electrons are completely filled up. To squeeze them any closer together, gravity would need to force electrons into energy levels that are already occupied, which is forbidden. The electrons resist this compression with a tremendous force, creating a pressure that is independent of temperature and powerful enough to halt gravitational collapse forever. There is a limit, however. If a white dwarf's mass exceeds about 1.4 times that of our Sun, a threshold known as the Chandrasekhar limit, electron degeneracy pressure will fail, and the star collapses catastrophically. For stars born with much more mass, the end is far more violent. After the iron core forms and fusion ceases, gravity wins instantly and overwhelmingly. The core collapses in less than a second, shrinking from the size of the Earth to a diameter of just a few dozen kilometers. This implosion triggers a titanic shockwave that blasts the star's outer layers into space in a supernova explosion. These explosions are not only spectacular, they are the primary cosmic events where elements heavier than iron, like gold, platinum, and uranium, are synthesized and scattered across the galaxy. If the remnant core left behind is between about 1.4 and 3 solar masses, it becomes a neutron star. Here, the gravitational collapse is so intense that it overcomes even electron degeneracy pressure. The electrons are squeezed with such force that they merge with protons in a process called inverse beta decay, forming neutrons. The entire stellar core becomes a dense ball composed almost purely of neutrons. These city-sized objects are so dense that a single teaspoonful of neutron star material would weigh billions of tons. What holds a neutron star up against its own colossal gravity is neutron degeneracy pressure, the same quantum principle that supports white dwarfs, but applied to neutrons. The physics here is truly extreme. But what happens if you compress matter even beyond the limits of a neutron star? Here, physicists enter a speculative realm, where the laws of nature are pushed to their absolute limits. It's theorized that under the unimaginable pressures inside a massive neutron star, the neutrons themselves could dissolve, breaking down into their fundamental constituents, quarks and gluons. This would create a state of matter called a quark-gluon plasma, a deconfined soup of free elementary particles. A further hypothesis suggests that this could then transition into strange matter, a theoretical substance even more stable than ordinary matter, creating an object known as a quark star, even smaller and denser than a neutron star. These are the frontiers of modern astrophysics. This all sounds incredible, but you might be wondering how we can possibly know any of this. We can't scoop a sample from a star's core. Instead, scientists rely on a sophisticated toolkit of remote observation and terrestrial experiments. The most important tool is spectroscopy. By analyzing the light from a star, splitting it into a rainbow of colors, astronomers can decipher its chemical composition, temperature, and pressure from the unique spectral lines that act like fingerprints for different elements. We also use astroseismology, which is the study of starquakes. By observing the subtle vibrations on a star's surface, we can model the structure of its unseen depths, much like geologists use earthquakes to understand Earth's interior. And perhaps most amazing of all is neutrino detection. Neutrinos are ghostly subatomic particles produced by fusion in the star's core. They interact so weakly with other matter that they fly straight out of the star at nearly the speed of light, carrying direct, unfiltered information from the core. By capturing a tiny fraction of these neutrinos in giant underground detectors here on Earth, we get a direct window into the Sun's fusion engine. From the roiling plasma that powers the cosmos to the bizarre quantum-supported cinders of dead stars, the journey of matter through a star's life is a testament to the transformative power of physics at its most extreme. It's a story that pushes matter to its breaking point and beyond, and in doing so forges the very elements that make life, our world, and our own bodies possible.